We need to determine the deflection curve for the simply supported beam subjected to a concentrated load at midspan, as shown in the figure. And once that we have the deflection curve, we need to calculate what would be the slope at A, or the rotation at support A, as well as the beam's maximum deflection. We are told that the flexural rigidity of the beam, which is the product of the elastic modulus and the moment of inertia, is constant. In problems where we need to determine the curve for the deflection of a beam subjected to certain loading condition, we are going to be using the discontinuity functions method. And the reason is because most of the times you're going to see that the bending moment diagram is discontinuous. Like in this case, you see the triangular shape shown on the screen represents the bending moment diagram of that beam subjected to a load at midpoint. And that bending moment diagram is discontinuous at midspan. So therefore the use of the discontinuity functions method is going to be useful here. How do we use this method? Well, we need to set up an equation that describes the bending moment along any point on the beam, and for that we need to draw the free body diagram of all the applied forces as well as the external reaction forces, and that's what we have here. So we calculated the reaction forces at the support. They are equal in magnitude, and their values are the load P divided by 2. In writing the bending moment equation, we are going to be using the Macaulay function that represents a concentrated load, since we only have concentrated loads in our free body diagram. And if you look at the diagram on the top left of the screen, the bending moment that results from a concentrated load P applied at A is minus P if the P is going downwards and P if it's going upwards. And then we have the Macaulay function with these brackets of x minus A. So the coordinate x minus the coordinate where the load is applied. So based on that Macaulay function, let's write the equation of the bending moment for this beam. And the first load that we have is that of the reaction at A. So following the same formula that we have on the top left, the load is going upwards, so it would be positive. The magnitude of the load is P over 2. And then we have the Macaulay function of x minus the coordinate where that force is acting, which is x equals 0. We proceed to the right and we find the concentrated load P going downwards and acting at midspan. So we would have minus P, the magnitude of the load, times the Macaulay function of the x coordinate minus the coordinate where it's acting, which is L over 2. And finally we have the reaction at the right support B. So we would have plus, because the load is going upwards, the magnitude is P over 2, and then we have the Macaulay function of x minus L. We can actually simplify this function based on the definition of the Macaulay function. So if we look at the last term here, and you refer to what a Macaulay function is, this term in the brackets is going to be 0 for any x coordinate that is lower than L, and then it would be whatever is inside the brackets if the x coordinate is greater or equal than L. So when we consider this particular term in relation to our beam, we are going to see that all the x's in the beam are going to be lower than L, which means that this term will go to 0. And for the particular point where x is equal to L, it will cancel as well, because it will be L minus L. So we can actually ignore the last term. Now, if we look at the first term here, again, all the x's in the beam are going to be greater or equal to 0. So we actually evaluate the function, and it would always be x minus 0, which means that we could just write it x. So the simplified equation for the bending moment would be P over 2x minus the second term, which is P, Macaulay function, x minus L over 2. So we have an equation for the bending moment throughout the beam. Now we are going to go to the beam equation that states that the second derivative of the deflection, which is the vertical movement of any point along the beam with respect to x, is equal to the ratio of the bending moment divided by the flexural rigidity. Since the flexural rigidity is constant, we are going to pass it on the left-hand side of the equation, and we end up with a second-order differential equation that is equal to the bending moment. So if we integrate the left-hand side of the equation twice, we will obtain V, which is the deflection, and for that we would have to integrate the right-hand side of the equation twice, so integrate the moment equation twice. So let's do the first integral. The first integral is going to give us the first derivative of V with respect to x, which is nothing else than the tangent of the deflection curve that is giving us the rotation. So how much that point on the beam is rotating with respect to the horizontal, because at the beginning it was horizontal, is going to move upward or downward, and as a result the beam at that point is going to rotate. So that's what the dV over dx is giving us. And we just integrate the moment equation, so we would have p over 2 times x squared divided by 2. This is where the p over 4x squared, and then the integral of the Macaulay function, again referred to the handout, but is integrated the same way we would integrate an x function. So it would be this term squared divided by 2, so that's where the minus p over 2 Macaulay function of x minus L over 2 squared, and then we have to add a constant of integration. We are going to do the second integral, so basically integrate the slope equation, and we end up with the deflection curve. Note that on the deflection curve we would have to add a second constant of integration. So before we can say that we have the curve that defines the deflection of this beam, we need to determine those constants of integration. So to do so, we have to look at the boundary conditions of the problem, which means that what are the values that we know of V and dV over dx at A or at B, which are the supports, or is there any other condition like symmetry, for instance, in this case, that would allow us to determine one of those two values. So the first thing that we are going to look is at support A. So we know that the pin at A is preventing translation along the horizontal and vertical, so we know therefore that the deflection at that point is going to be equal to 0. So we know that at x equals 0, V is equal to 0. If we substitute that into the second equation, we are going to find out that constant of integration 2 is equal to 0. We also know that this problem is symmetric. It's symmetric with respect to the boundary conditions, symmetric with respect to the loading applied at the middle. So we know that the beam is going to deflect something like that with a maximum value at midspan, which means that if the deflection is maximum at midspan, its tangent is going to be 0, dV over dx is going to be 0, which is nothing else than the slope is going to be 0. So therefore, at x equal L over 2, we have that the slope is equal to 0. We substitute that into equation 1, and we find the value of the constant of integration 1 as minus PL squared over 16. So we have determined both constants of integration, substitute into equations 1 and 2 in the previous slide, and these are the final equations that will give us the value of the slope or tangent to the deflected curve, as well as the value of the deflection at any point x. Now, to determine the slope at A, we have to substitute x equals 0 into the equation of the slope, which is equation 1. So by just substituting x equals 0 there, we find out the slope at A, or the rotation at A, would be minus PL squared over 16 times EI. Note that we would have to bring the flexural rigidity on the left-hand side of equation 1 to the right side, so we have to divide everything by the flexural rigidity. Note that the negative sign here indicates clockwise rotation. If we would have a positive value, the rotation would be counterclockwise, meaning that there would be a positive slope. To determine the maximum deflection, we are going to substitute into equation 2 x equal L over 2. Note that when we substitute the value of the coordinate into the equations where they are Macaulay function terms, we have to evaluate that coordinate x with respect to the other value on the Macaulay function. So for instance, on the first term, we would have x cubed, so it would be L cubed over 8. That in itself was not a Macaulay function. But if you look the second term that would come here, x is equal to L over 2, so therefore we evaluate that function. It would be L over 2 minus L over 2. It goes to 0, so we don't have it here. And then we have just substituted x L over 2 into the term that was corresponding to the first constant of integration. So we simplify that expression, and we find that the maximum deflection would be minus PL cubed divided by 48 times the flexural rigidity. And the negative sign here indicates that the deflection is going downwards. So when we have a positive sign for V, deflection is going upwards. When we have a negative sign, the deflection goes downwards.